I was like, okay. Okay. Second chance.
All right, we're going to start off first of all, just a little warm-up problem. So I want you to read this question and answer it. It says, which costs more per pound according to the graph, peas or cabbage? And don't just give me a one-word answer, but I also want you to explain how you know which one it is. So use just a few seconds to do that, and then we're going to go over it. You can just add that to your previous bell work.
Very good. Very good.
You get interpreting.
Now I see several different answers, but that's okay, because I want you to be able to explain why you said what you said. How many think it's the cabbage that costs more per pound? It's okay, don't change your answers, it's okay. And why did you say that, Parker? Why did you say that you thought the cabbage was more per pound?
Because it's sloped more towards the cabbage than the peas on pounds.
So it sloped more towards the pounds, is what you said that? Okay. Someone that said that the peas cost more. Tran, why did you say the peas cost more?
I said the peas cost more because no matter where you are on the graph, the slope is higher on the cost range.
Okay, what do you mean by the slope? The slope is higher.
How diagonal the line is, because if you go to the very tip, the peas slope is higher than the cabbages.
Okay. It is the peas. It is the peas. Because here, what axis is this? The x-axis. So the x-axis is talking about pounds. As pound is increasing, what's happening to the cost? It's also increasing on both of these, which means if the pounds and the cost for the cabbages here at that same poundage, the cost for the peas is what?
Higher.
It's going to be higher. Okay. Everybody understand that? Okay. Yesterday we talked about graphing linear equations. Just remember, what were some of the ways that we can use graphing linear equations? What did we do? We just start graphing? What did we do to graph linear equations? Ryan, what did we do to graph linear equations?
We use some tables.
Okay, we use tables, function tables. What else could we use on that?
We used ordered pairs.
Ordered pairs. What does the ordered pairs tell us, Bailey?
It tells us like the number of the x, like what number it's going to be on the x and y axis.
The x and the y axis, very good. So we use the ordered pairs from the tables to graph that. What else did we talk about?
Fractions.
Fractions, okay. Do we use fractions to graph them? What did we talk about with the fractions?
They were slope. Like slope is a fraction.
Slope can be used as a fraction. Why can it be used as a fraction?
Because slope is a number over a number, and so it's rise over run.
Okay, so it's a ratio, which is a fraction. Okay, very good. So today we're going to elaborate on that a little bit more, and we're actually going to use a task to investigate rate of change in slope. So we're going to take it just a little bit further, and we're actually going to use triangles, similar triangles. What do I mean by similar? What do I mean by similar? Trent?
They're proportional.
They're proportional. What does proportional mean?
That if you enlarged it, it would be the same as the other triangle. If you shrank it, it'd be the same as the other side.
Okay, very good explanation. So we're going to see why similar triangles is going to help us explain why slope is the same between any two distinct points on a non-vertical line. Show me with your hands, what does vertical look like? What does vertical look like? Show me with your arms. Is it like this or is it like this? What's vertical? So it's straight up and down. So anything that's non-vertical, which means it's not going to be straight up and down, we can see how the distance between any 2 points on that non-vertical line is going to be the same. Then from that, we're going to derive the equation y equals mx for a line that goes through the origin. Who can tell me where the origin is? What is the origin? Taylor, where's the origin?
Right where the x and y axis meet, right in the middle.
So that order pair is going to be what?
0, 0.
0, 0. Very good. So at the origin, it's just going to be y equals mx. And if for a line that's not through the origin, it's going to be y equals mx plus b. How many like music? How many like music? I like music. What are some ways or places that we use music or see music or hear music? What are some different places that we would have music?
In your car.
In your car, just ride them around, listening in your car. What's another place?
In an elevator.
In an elevator, when you're sitting in the elevator, you hear Taylor, what's another one?
At home.
Just at home, okay. What are we gonna say?
At a dance.
At a dance. Sometimes we have school dances.
When you go shopping, a lot of stores play music.
Very good. At stores, a lot of times they'll have music. Well, we're not going to talk directly about music, but how many of you all buy CDs sometimes? You all buy CDs? Okay, so we're going to look at how, on a graph, how we can relate the price of CDs, and they're not always the same price, but we're going to just give like an average price of a CD versus how many CDs you may purchase or you may have. So we're going to use that to do a little investigation. And in our investigation today, we're going to have several different segments. First, when I pass out the task that we're going to work on, I'm going to give you a few minutes of private think time. That just means that for the first few minutes, for 5 minutes, I just want you to kind of look at the sheet, answer the first few questions, and just kind of see what you can think about on your own. Then after we have that private think time, we're going to then get in our small groups that you're already in, and y'all going to discuss what you've already found on your